In section 9.3, we look at tangent planes. Consider what we did in Calculus 1 when we're looking at potentially complicated functions. In Calculus 1, we considered tangent lines to approximate the values of these functions. And if you have enough of these tangent lines, you can use these tangent lines to approximate a potentially complicated function f of x. In this section, we do something similar. In this section, we'll be looking at our functions f of x, y, which we can think about as being surfaces in 3 dimensions. And what we could do is consider planes to approximate these surfaces. If we have a function f of x, y out in space, we can consider getting the equation to this plane by looking into the point that's on the plane. So that purple point has coordinates x, 0, y, 0, z, 0. And then a point that lives on that plane. So let's say that point has coordinates, general coordinates x, y, z. If you were considering the vector that connects these two points, this vector can be considered the vector x minus x naught, y minus y naught, z minus z naught. And then we're going to consider a vector going out of this plane that makes a 90-degree angle with the blue vector on our plane. For this purple vector going out of the plane, let's say it has elements A, B, and C. In a more advanced calculus class, I would be able to show you that this guy can be a vector that satisfies these properties, that makes a 90-degree angle within that plane, can be obtained by the formula, the partial derivative of f with respect to x at AB, or let's say x naught, y naught, with a negative partial derivative of f with respect to y at x naught, y naught, comma 1. So if I want a nice formula for this red plane, I can take the dot product of this vector in purple and this vector in blue, and because these guys make a 90-degree with relative to each other, that dot product should be 0. So in other words, when I take negative partial derivative of f with respect to x at x naught, y naught, and multiply it times x minus x naught, and add negative partial derivative of f with respect to y at x naught, y naught, and multiply that times y minus y naught, and multiply 1 times z naught minus, z minus z naught, that should give me 0. So again, these guys right here make up the elements of this purple vector. And these elements right here make up the elements of my blue vector. And the left-hand side represents the dot product of those two vectors. And because they're orthogonal, they make a 90-degree angle between each other. That dot product is equal to 0. So we can take this equation and rewrite it into more convenient way. So if I take this equation and solve for that z by moving this element over to the right hand side and this element over to the right hand side, I would have that z is equal to the partial derivative of f with respect to x at x naught y naught times x minus x naught plus the partial derivative of f with respect to y at x naught y naught times y minus y naught. And then we'll have this equal to z minus z naught. And if I move that z naught over to the right hand side, I could cap this off with a plus z naught. But if you're working with a function f of x, y, that z naught is really going to be the value of your function at x naught, y naught. So this is a formula for the tangent plane at x naught, y naught. Sometimes this z is written as L of x naught, of x comma y, and it's known as a linearization of f of x, y at x naught, y naught. And this function provides a pretty good approximation to the function f of x, y when your x's and y's are really close to x naught, y naught.